Alright, hey there guys, I'm here with the second video, which is about how to extract the proportionality constant from your experiment 3 data, because you'll need that information when you're doing your 2-sample t-test with your data from experiment 4, and you'll need all that for your lab report. So let me kind of work backwards and talk about what we mean and what we're doing. Alright, so in the last experiment, experiment 3, we were investigating two things, right? We're investigating that the height is equal to 1/2 gt squared, right? Where t is the time of flight. And before we were looking, right, for this exponent of 2. And we were trying to find that, we got as close as we could, right? Whatever. Now, we did the same thing, right, for the period of the simple pendulum, where the period is equal to 2 pi square root of L over G. So we were trying to find that square root, right? That power of 1/2. Well, now what we're trying to do is understand the proportionality constant. And so what I mean by that is, let's take a look at the time of flight equation first. So in this time of flight equation, if we know that it's proportional to t squared, then that means the only thing we don't know, right, would be this. So let's call 1/2 g, let's just call that c, for example. So we know that h is equal to c times t squared. That's what this part of the experiment is about. We're trying to find this value c, and once we find that value c, we can actually find out what the value of g is. We should know that g is equal to 9.8 meters per second squared, right, approximately. And we're just trying to verify that we get that value regardless of the kind of experiment. So meaning it doesn't matter if you change your height or length, it doesn't matter if you change your mass, we should always get a value of 9.8 meters per second squared. And so that's what we're trying to do with our experiment 3 data, and what you'll be doing with your experiment 4 data. So I'm going to work out for you guys how we go about doing that. So let's take a look at our Excel data here. So what I have here is the same data that we had from the last video, right? So we have our trials 1 through 5, we have the best times, their uncertainties, the best heights and their uncertainties. And now we are tasked with trying to understand how we can get the proportionality constant, 1/2 g, from this information. So we're going to assume that we already know that the height is proportional to t squared. So we're going to take these t values and we're going to square them, because we know that this height is proportional to these values squared. So very simply, we're going to go into this box here, click the equal sign, click the first data point up there, and then we're going to raise it to a power of 2, click enter. And same as before, we click and drag, so apply the same function to the other data points in that table. And of course, you can check to make sure, right? But you can trust and believe that it's done it correctly. All right. Now we need to get the uncertainties for these squared values. Now, warning, it is not as simple as taking these uncertainties and squaring them. That is not what this means. There is actually a formula that you need to use in order to do this, and they kind of talk about it in the manual, in the modules for this part of the lab. So, for example, for the period of a simple pendulum, we know that t is proportional to the length to the 1/2 power. So t is equal to some proportionality constant c times L to the 1/2 power. So for this particular data set, we would want to change our L values to L to the 1/2. But then we need to calculate a new uncertainty for L to the 1/2. To calculate that, we use this principle here. Say that we have some value u, which is equal to a function of L. And that function of L is just square root of L. If I want to find the uncertainty, right, in square root of L, I have to first take the derivative of this function, right, and multiply that by the original uncertainty in L that we had before. we can apply the same idea, right, to the time of flight that we're looking at. So we know that h is proportional to t squared, where h equals some proportionality constant c times t squared. So we want to find the uncertainty, right, in t squared, right? But how do we go about doing that? Well, we use the same setup that they had before. So we want to find the uncertainty u, which is t squared, right, which is a function of some time t. And in this case, right, f of t just equals t squared. So u equals t squared. That's the function we're working with. Now, we're going to apply the same exact formula that they had before. So the uncertainty, right, in u, or t squared, is equal to du d of f, right, times the uncertainty in t as it was originally, right, not the new one. So what we have to do now is take the derivative of this function right here. So if we take the derivative of this function, we get du equals 2t. So that's going to be what we have right here. So the uncertainty is equal to 2t times the uncertainty in t. And we can replace u with what it equaled originally. So therefore, the uncertainty in our t squared values is equal to 2 times that original t value times the uncertainty, times the uncertainty for that original t value. That sounds complicated. I know it's a lot, but just trust me that this right here is the formula that we're trying to use. We're going to apply that same formula to the data that we have in Excel. So again, before, we have our formula for the uncertainty of t squared, which is equal to 2 times the original t value times the uncertainty for that t value. So we're going to go on ahead and use that formula in our Excel data. So we do equal sign 2 times the original t value, right, times the uncertainty in that t value, and we get that number right there. We can go on ahead and just click and drag to apply the same function to all the other values. Now, we don't have to make any changes to our values for h best or its uncertainties. We're only concerned with raising our t best to the second power, because we're assuming that we know what the proportionality is between h and the power of t. So we're just going to go on ahead and just copy and paste the same data that we have here. And we'll be able to use that stuff when we're going to go on ahead and make our plots. All right, so this is our new trial data, right? In the context of, we know that h is equal to 1/2 gt squared, but we don't know what 1/2 g is. We're trying to find 1/2 g. So we're going to take our t best values that we have here. Let's redo that again. Sometimes when you're copying and pasting into Excel, you might have to specify that you want just the values. So there we go. And we'll take my h best data as well. Okay, so now, just like before that we did in the previous video, we're just going to make a plot of this data. And we're just going to make a regular old plot. We're not doing any log plots, because a direct fit is the easiest way to get the proportionality constant out of our data. It requires less math, requires less work, and we will do that right about now. So remember, again, to make your plot, you drag the data you're hoping to make a plot of, and remember, the first column will be your x-axis, second column will be your y-axis. For us, the time of flight, or time of flight squared in this case, is our x-axis, and the height is the y-axis. So this is the correct order for the columns. So we go ahead and click the box here, click charts, click scatter, we get our scatter plot. Just like before, we have to go on ahead and put the trend line in, label the axes, blah blah blah. I'm going to go on ahead and do that stuff for you guys, and you just sit tight and wait a second. All right, so I have officially titled and labeled my axes accordingly. Whenever we're looking at y as a relationship or function of x, in our case, the y-axis is the height. So we're looking at height versus the squared time of flight, where my y-axis is labeled as the height in meters, and the x-axis is labeled as the time, but in seconds squared, since we, squared the time, so it's seconds squared. Now we're going to go on ahead and add our trend line to this equation, right? And we're going to click more options as well, because there's a few different things we're going to want to do, right, as we attach this linear fit trend line. So if you take a look at the modules, right, it does tell you what we're going to end up doing when it comes to plotting this data. So after we plot, right, y versus x, or y and x, you know what I mean. After we plot that, we have to enforce a zero intercept when theory predicts that y of 0 equals 0, reducing uncertainty and preserving your absolute measurement errors in y. So what they mean by this, right? Because we're looking at height versus time of flight, the physical thing we expect is that if we have a height of 0, your time of flight should be 0, meaning that your trend line should pass through the origin. This current trend line does not pass through the origin. It passes somewhere above. So in our options for the trend line, we're going to click Set Intercept, and it's going to be set at 0. This makes a brand new trend line that actually does pass through the through the origin. X equals 0, y equals 0. Now we're going to click Display Equation on Chart and look at the slope for this particular zero intercept trend line. And we see we have a slope of 4.6297. Now, unlike the previous experiment, the slope that we're getting here is not finding the exponent, because we already know what the exponent is. It's 2. But the one thing that we don't know is the proportionality constant, right? 1/2 g. That's what we're solving for. So this is basically 1/2 g. So we can write this as our C best. So C best is equal to 4.6297. Well, now that we have our C best, we need to translate this in terms of what G should equal, right? And I'm going to go on ahead and show you guys exactly how we make that relation. So I'm going to switch over to my iPad, and I'll see you in just a moment. All right, so we are back here on the iPad, and I'm going to explain to you guys how we get our value of G, right, the constant of gravitational acceleration on Earth, how we get that from this value of C, right, the proportionality constant. So again, remember that we had that the height is equal to 1/2 g t squared. We have the t squared part, so what we don't have is the 1/2 g, which we called C. So you could really just say that C equals 1/2 g. Well, if I want to solve for g, it's just a matter of, simple, algebra, right? You just put g on the other side. So that means, therefore, that g is equal to 2 times C. So if we take our C value and we multiply it by 2, we will get our G value. So we're going to go on ahead and put that same thing into practice, right, for the value of C that we've already extracted from our plot. So we go on ahead, we've got our C best, we know the equation for G, so we hit our equal sign, put in a 2 times C. And we get a value of 9.2594. Now remember, the constant of gravitational acceleration on Earth is 9.81. This is pretty close. So we're actually, we're doing it right. We're seeing that the data is representing the physical concept that we were trying to understand from the experiment. And we're also seeing the importance of enforcing this zero intercept, right? Ensuring that the trend line crosses through the origin. Otherwise, we would get a G best that is much different, right, than what we do have right now. Now, just like in the previous video, when we report a quantity that's measured, we have to report it with an uncertainty. This is not an uncertainty. This is just the best value. To compute the uncertainty, we need the maximum slope, the minimum slope, use the uncertainty equation, blah, blah, blah. So we're literally doing the exact same thing that we did in the last video, but for this video. So first things first, we need to add the error bars, right, to this plot. So we're going to go on ahead, click the plus sign, error bars, go to more options, because we need to do custom error bars. The horizontal error bar represents the x-axis, which is time. So we're going to click custom, specify value, and we're going to use these values for the positive and negative ends of our error bars. All right, now we need to get to the vertical error bars as well. So I'm going to try to click them if I can. Maybe not. There we go. All right, hit custom, specify value. Now the positive, or the y-axis rather, is the height. So we're going to take these uncertainties right here. And there we go. Now we have the error bars for the data points that we have here. Now, the next part is, of course, to make the error boxes, quote unquote, in order to get our minimum and maximum slopes. Now, when you're actually choosing the corners you want to use for your error boxes, you don't have to specifically use top left corner, bottom right corner. You don't have to use those specific corners. You need to use the corners that give you a slope that is consistent with your data. For the last experiment, when you were getting the trying to find the exponent, right? It's fine if you got some negative slopes. We'll leave it as it is. But for trying to get the proportionality constant, we really want to make sure we don't have negative slopes, because that is not physically, consistent with the actual theoretical model of what's supposed to be happening. So let me tell you what I mean by that. So typically, right, we would want to use this furthest left point and this furthest right point as the 2 points, right, to put error boxes around to get the minimum and maximum slopes. So this point right here is this trial 4. And this point over here, it is, let's just zoom in to see what its values are. There we go. All right, that right there, 0.38, 1.69, that is 0.1, right? So we're using trial 4 and trial 1. So 4 is here, 1 is there. So typically, we would use the top left corner of trial 4 and the bottom right corner of trial 1 to get the minimum slope. But let me illustrate for you what would happen if we actually did that. So I'm just going to get the pen out here, right? And I'm going to go on ahead and draw on this. So for trial 4, the top left corner is about, I'd say, right over here. And for trial 1, the bottom right corner is about right here. Now, if we were to draw a line, right, from one point to the other, we would get a very negative slope. We do not want to have a negative slope for this particular part, right, of extracting the proportionality constant. That's just not physically consistent, and it's going to really mess up the data that we get. So what this means is you're free to choose the different corners of the error boxes you're using so that you do get a minimum slope, but it's not negative. And so the choices what we want to make in our case, right, are what I've put here. So for trial 4, we're going to use the bottom left corner instead, while still using the bottom right corner of trial 1. And once more, I'll illustrate why. So for trial 4, the bottom left corner brings you all the way out here. And for trial 1, the bottom right corner brings you all the way over here. If I draw a line between those 2 points, I get that slope right there. Pretty much an ugly line. Sorry about that. I can kind of redo it. Right? We get that slope. That is a very, minimal slope. It's a very, not very slanted line. It's not very steep. And when we compare this to the slope for the maximum line, which I can show you very quickly, for the maximum slope, we use the bottom right corner of trial 4, which is right about here. And we use the top left corner of trial 1, which is about right here. And then drawing a line between those two, we see that the maximum slope has a line like this. So both of these slopes are positive, and they are indeed minimums and maximums. So you can in fact choose the corners of your error bars, right? So long as you are, within your error box, right? If your error boxes overlap with each other between your first and last data points you're using, then you can't make those different choices. You have to stick with the top, left, bottom, right. But if you don't have overlap, you can make some changes so that you still get a minimum and maximum slope without dropping into negative values. So we're going to use the points that I've just talked about right here in order to get our minimum and maximum slopes. And even though I've already showed you how to do that in the previous video, I'm still going to go through it one more time, just for those who've maybe been having a hard time doing so themselves. Alright, so for trial 4, we're going to the bottom left corner. So because we're going to the left, we have to subtract. So we take the value of t squared for trial 4, and we subtract the uncertainty to go to the very left side of the box. And because we want to go to the bottom, we have to take the y value for trial 4, which is this right here, and we have to subtract so that we can go downwards. This gives us the bottom left corner, right, of trial 4. Now for trial 1, we want to go to the bottom right corner. Because we're going to the right, we need to add. So to trial 1, we go to the t squared value, and we add the uncertainty. And because we're still going down to the bottom, we're going to go to the y value for trial 1 here. And we're going to subtract the uncertainty. All right, so that gives us our y2, y1, and x2 and x1. So just like in the last video, you're using your point slope formula to get the slope. So y2 minus y1 divided by x2 minus x1 gives you the slope. Right? In our case, that slope is our proportionality constant, c, and we're getting our c minimum. So let's go on ahead and just like last time with the order of operations, y2 minus y1 divided by x2 minus x1. Right? And there is our c minimum value. Now, just like before, we want to transpose our c minimum value into our g minimum value, right? And remember that our g value, right, is equal to 2 times the c value. So we just do equals 2 times c, and that is our minimum value of the constant of gravitational acceleration. Now we have to do the same kind of thing, but for calculating the maximum proportionality constant, the maximum slope. For this one, we have that trial 4, we're using the bottom right corner. In trial 1, we're using the top left corner. At this point, I fully expect you to already know how to go about performing these calculations to get the x and y values. So I'm going to go on ahead and do that to get the slope and to also get the g max value, because you should already know the formula by now. I showed it to you. G is just equal to 2 times c. So whatever you get for c, multiply that by 2, and that's going to be your g value. Alright, so I am back after having performed the relevant calculations to get the bottom right corner of trial 4, top left corner of trial 1, using the point slope formula to get c max, and then using the fact that g equals 2 times c to get the maximum value of g, which ended up being 96.135, blah, blah, blah. Yeah, that's really large. That's just how it happens, guys. When you have really large uncertainties, especially when you're just taking old data and you're squaring it and you're just extrapolating it, and forcing a zero intercept, right? You're doing a lot of assumptions that are supposed to reduce your uncertainties, but can actually blow them up in some ways too. So we end up with, the numbers that we get here. But anyway, I digress. What we need to do now is we need to compute, of course, the uncertainty in our proportionality constant. And you just use the absolute uncertainty equation. So we do equals C max, minus C min divided by 2. And there is our uncertainty in the proportionality constant. Right? And then, of course, C measured, you have to report that properly. Now, your uncertainty is supposed to be reported, up to one significant digit. And we started off with, 2, at most 3. So I'm going to report this to, let's say, 1, 2, 1.6, I'll report this to 2 significant digits. So C best to 2 significant digits would be 4.6. So this is 4.6. I'm going to get this plus or minus sign from here. 4.6 plus or minus. And now we have 2, 3.6. The 6 rounds a 3 up to a 4. So I've got 24. So 4.6 plus or minus 24. That's a really large uncertainty. Now this part is what it is, but what we really care about is getting our value of the gravitational constant of acceleration. So we need to compute the uncertainty, right, in our G value. Well, we have G max and we have G min, so we just do the same thing that we would have done before. So we have equal sign G max minus G min divided by 2. There's our uncertainty, and now we can finally report our measured value of G for the best value plus and minus the uncertainty. And we're going to do this one to, let's say, 2 significant digits. So G best to 2 sig figs would be 9.3. That 5 rounds up to 2, so 9.3. We got plus or minus, and 47.34 to 2 significant digits is just 47. So I got 9.3 plus or minus 47. That is a very large uncertainty. Now, the good thing is, right, remember the number we're looking for is 9.81. We got, 9.3 plus or minus 47. So with the plus 47, you do get to 9.81. So we're pretty close. Honestly, even just our G best, before even calculating our uncertainties for G, that was pretty close to 9.81. So we are seeing how scientists and physicists, especially in this case, are able to extract these well-known and well-verified quantities from the experimental data that they've done. And of course, had we used even more precise methods like the Pascal machine, we probably would have had a G best of like 9.7, 9.76, or 7.9, maybe even 9.81 for all we know. Right? But the large uncertainty, of course, comes about due to the imprecise human errors, right, and human methods that we use for getting the data. But this is how you go about, right, getting the proportionality constant out of your experiment 3 data, and then taking the value of G out of what you have from the proportionality constant. Now, you're going to do a similar sort of thing when you're doing the period of a pendulum. Right? You're still going to get your C best and your C min, right? But you're still going to have to make sure that when you calculate your new values of the length, not the time for the pendulum, you have to make sure you calculate your uncertainties correctly. The way of how to do that for the period of a simple pendulum, it's in the module, guys. So when you're applying the steps I just did in the video to your experiment 3 data for the period of a simple pendulum, he literally tells you right here how to do that. This is 4-2, evaluating constants of proportionality. He tells you how to calculate the redone value of your length from your experiment 3 data. Right? So go ahead, use the resources here, use the video, right, and make sure you guys get the value of G, right, from both your free fall and period of a simple pendulum data from experiment 3, because you'll be needing that information with the value of G you get from experiment 4. And now that I've showed you how to get, right, your value of G from your experiment 3 data, the same steps still apply for experiment 4. So when you're going through the experiment 4 workbook and it tells you, get T squared, get the uncertainty in T squared, it's the same things that I just did here, right? And it's the same things that is right here in the modules, right, for the period of a simple pendulum. So you have the resources, You have the information. I fully expect you guys to be able to do it now up to this point. Of course, if you still have questions, you encounter some confusions or some errors, bring them to me. But for the most part, this is about it. The most difficult thing I think you'll encounter is choosing the corners of your error boxes properly for your experiment 3 data so you don't end up with negative slopes. So if you find you might need help with that, come see me in office hours. Other than that, good luck, right? I think you guys would do great, and just shoot me a message otherwise if you're having a hard time. But that should be about it, and you guys take care.